all for coming and participating in people. I would like to introduce Dr. Burgman, who was the chief and emeritus professor of risk analysis and environmental policy in the Center for Environmental Policy at the Imperial College in London, as well as the editor-in-chief of the journal Conservation Biology. Dr. Burgman is also part of the Adrian Clark Department of Botany at the University of Melbourne in Australia. He also works as an expert judgment on ecological modeling, conservation biology, and risk assessment. He has written models for biosecurity, medicine regulation, marine fisheries, forestry, irrigation, electrical power utilities, mining, and national park planning. He received his Bachelor of Science from the University of New South Wales, the Masters of Science from Macquarie University, and his PhD from State University of New York at Stony Brook. He also has worked as a consultant, ecologist, and research scientist in Australia, the United States, and Switzerland during the 1980s before joining the University of Melbourne in 1990. He joined CEP in February 2017 and has published over 250 referred papers, journals, books, book chapters, and 7 authored books. He was elected the Australian Academy of Sciences to the Australian Academy of Sciences in 2006. And today we are honored to have Dr. Judgement as the new director of the Isabella Calcare Abbott School of Life Sciences and professor at the University of Hawaii at Manoa.
Thank you very much, and I'm sorry that was so long. Oh. Wow. I do like this. Okay. I see a few faces here that were present when I interviewed for the job. So if you've seen this talk before, you really should go. It's just going to be the same stuff because I guess I insisted that I do a reprise rather than something special and new, which I could have done on much more interesting topics. But nevertheless, you're here, and if you feel obliged to stay, I'll make it as interesting as I can. I'm going to move through some of this reasonably quickly because there's a lot to talk about. But we can go back and just revisit any slide you want when we come to. Okay, I'm going to talk about 16 directly. Why do we need experts? Why do they make mistakes? Who is an expert? There's this thing called wisdom of crowds. And then the core of the thing, which is what you should do. And I just want to make this point at the start. If you're not doing this, you are being professionally negligent. So there's about 5 minutes, about 3/4 of the way through, where you actually have to listen and take notes. Because if you're not doing this and you're asking people for facts and the facts matter, then you're wasting resources and wasting precious resources in making poor judgments or poor estimates of things that you need to know in order to make a decision. And then we'll look at a little bit about the performance of the systems that we're going to talk about. So why do we need judgments? Well, this is an excerpt from an international standard biosecurity provisions, that is decisions about commodities and trade and people and the pests and diseases and pathogens that accompany them, must follow evidence-based procedures consistent with international standards. But what is evidence-based? In a circumstance in which decisions are imminent, consequences are substantial, and the evidence will require the data and the understanding are unavailable or incomplete. For example, because the event you're trying to estimate is in the future, or it's simply not known, and yet the decision is imminent and serious. And you've all confronted those. So what are you supposed to do? Here's an example. We actually constructed this example before COVID, but it became a tool to use in COVID. There's a caseload for a new disease. There's some degree of immunocompetence. There's some rate of infection. And some of these people die. Some of these people get treated. Some don't. Some get sick, and then some of these die. And we're trying to minimise this, we're trying to minimise that. And how do you do this if you don't know what the infection rate is? Because we didn't know how transmissible this disease would be. It was new, it was out of a place we hadn't heard of in Western China, and we had to yet estimate this parameter to make decisions about who should be vaccinated, how often they should be vaccinated, and so on. And it made a difference to thousands of lives, thousands of early deaths. So this is where the rubber hits the road. We make similar decisions about biosecurity. Shall we allow this trade or not? Do we allow this person to come in across our borders or not? They see come sick. All those decisions are routine decisions that affect us. So we need experts to estimate simple, verifiable facts, and to predict the outcome of events and explain their reasoning in predicting the outcome of events or events. So we are just talking about that subset of things that is numbers or yes/no answers to questions that are, in theory at least, verifiable with external data. So things what we might call facts. How many adults are in this room? You may not know if they're sitting in the front. They ask you to guess, and you can make some reasonable guesses. Less than 100, it's more than 2, but you might get it exactly right. Now, you'll sometimes ask an expert, there's this prevailing tendency to ask an expert, what's the best course of action? How should I manage this problem? And to answer that question, you need to know the person to whom you're providing advice, as well as you know yourself. You need to know, are their kids sick? Do they want them to have private education? What are their aspirations for their own careers? And so on and so forth. And really, you can't answer that question. So if you ask it, you get what you deserve, which is just random noise and probably costs you money. So we're not going to travel this path. That's not what experts are for. So what are they make mistakes? They may have ate lots and launching rockets and allowing cows to live near a testing station in the United Kingdom, introducing frogs to control bugs in Australia, to telling people not to move out of their homes when there's a potential for an earthquake in Italy, launching new financial hedges. All of these decisions, these particular decisions, were affected by expert judgment that turned out to be wrong and led to very serious damages to people, to the environment, to the financial systems. It really illustrates how we might find ourselves if we are asked to make a judgment or provide advice and we get it wrong and someone dies or a species goes extinct or a fishery collapses. And we'd be thinking, well, am I responsible for that? Should I be held accountable for that? If I get it wrong and a fishery collapses, can they sue me? If I say to people, don't move out of your homes, the chance of an earthquake is small, stay at home, and there's an earthquake and 100 or so people die when they ordinarily have got into their cars and slept in their cars and have lived. Am I responsible for that? I could talk more about that, but we don't have time. So here's an early experiment, 1975, the earliest experiment I can find in which they asked 7 experts for their best estimate and some confidence intervals, an interval such that they are quite sure, that's the words they use, that the truth lies within the interval. And you can see that this person was very sure of themselves and very accurate. This person was very sure of themselves and very inaccurate. Over here, we've got person number 4 who was worst over here, there's a test over here. There are a lot of features in this very early, simple experiment that have been replicated now thousands of times in other experiments. This dotted line represents the truth. And you can see that even though they were very sure their interval enclosed the truth, only 2 enclosed the truth here, and none of them enclosed the truth. This is a standard result from studies of experts. We are, despite the fact we feel as though we're very hesitant, we don't like to tell what we don't know, and we like to be scientifically robust, we are in fact heroically, consistently overconfident in our knowledge. We know far less than we think we know. about the facts within our domain of expertise. We should be aware of that. Should be, as some of the social scientists say, we should express greater humility about things that we think we know. And there's other things. Experts generally are confident. Averaging experts doesn't necessarily converge on the truth, as would be the case of the same experts are always reliable, and there's no clear relationship to how confident they are and how accurate they are. So, this is reflective of the work done by Daniel Kahneman and colleagues. Daniel Kahneman, of course, got the Nobel Prize in 2002 in economics for this. The judgments are uncertain because we are frequently confident, we frame things differently, anchoring pervasive and pernicious and very influential psychological things in which your judgment about a fact will be coloured to an extraordinary degree by a number you have just heard, whether that number has anything to do with the problem or not. If I were to ask you for some quantity and in your domain of expertise, and as you walked into the room, I commented along the lines of, I think everybody here is over 5 feet tall. But number 5 would stick, and you would anchor off that number, and you would think, oh, that won't happen to me. And it is remarkably effective in altering your judgments about what you think facts. How well you understand the issues, your level of personal experience, how dreadful it seems, all of these things will affect your judgments about facts, and you will be largely unaware of the effect of those things when you make those judgments. And scientists are just as susceptible to these things as anyone else. And so Daniel Kahneman, he is getting his Nobel Prize at Princeton, holding a glass of champagne. Gertie Grenzer, a very famous psychologist, worked on similar things. Leads to a kind of pathology of judgment. Insensitivity, same size, draining effects, outcomes, angry, unsuccessful. So this is, I like this one, I'll just mention one in some detail. Law of small numbers. Daniel Kahneman and his buddy Amos Tversky call it this because in a tongue-in-cheek reference to the law of large numbers in statistics in which you converge on the truth of the same lots. And the law of small numbers is that scientists, experts, various kinds, will invest in the numbers that they personally collect a great deal more confidence than those numbers warrant. We tend to try, if we collect 3 or 4 numbers out of a stream, we think, oh, I know what I'm doing, they're roughly right. Someone else collects them, now I'll be much more suspicious of their numbers, but I'm good. This kind of self-promotion, a better word, appears in all kinds of domains, in molecular biology and bias in cell biology, for example. You might think, no, there's a key there. We did a study of the reliability of labs in evaluating PCRs for a particular contaminant that was arriving on various kinds of plants coming into Australia. We sent blind samples, both positives and negatives, to a whole range of labs, and 4 of the 5 labs, four of the labs, they're all accredited, all approved, all tested. 4 of the labs were pretty good, and 1 of them was terrible. And yet all 5 people felt confident in their skills and their reliability in making assessments and their ability to discriminate false positives and false negatives and all of that stuff that PCR labs do. And yet the error rate in one of these labs was such that if you sent something there, your chance of getting it right was about 1 in 3. Because of contamination, cross-contamination, mixing up with samples, just sloppy scientific practices. They didn't realise we're sloppy. Okay, so who's an expert? We do know, and this is another result that's been replicated many times, that if you grab experts who understand the question, who have some sort of qualification, some background in the topic, who are at least arguably some sort of expert, if you ask them to estimate parameters within their field of expertise, they'll be closer to the truth, this is distance from the truth, than lay estimates. And these are examples from people who all have master's degrees. These people are trained in biosecurity, these people are not. And these people are asked questions, both the groups are asked questions about biosecurity issues. But they didn't know. We knew the answers, they didn't, so we could calculate how close they were to the truth. Experts do better. And that's warming, heartwarming, reassuring. But they haven't done that much better. No, they haven't done massively better. The lay people who had no prior knowledge of this domain did okay. They weren't terrible. You could say, well, they were smart. No, so you can come back to that. So conventionally, expertise, defined by qualifications, years of experience, track records, publications, memberships, esteem, peer recognition. These are the sorts of things that you would say to a court if you were in legal proceedings and you had to establish your credibility as an expert witness. I've done this, I've done that. But what's the matter with expertise? We were asked this once. So we went straight to our friends in philosophy, in epistemology, and said, well, what's the domain of expertise? And they went, I don't know. I don't know what philosophers have been doing for the last many thousands of years, but they don't do anything useful because they should have answered this. Which expert should you use if you haven't come up with one? Should you assess how well they're recognised? Should you assess their status? What qualifications are essential? How many years experience should you look for? And then, once you've got an expert, how many questions can you ask them? How do you assess their performance? How should you have the bid? You should have two experts and they don't agree. How do you reconcile their different opinions? And this is encapsulated in a question that we were asked in 2008. How do we know we have the best possible expert advice? Again, a really good question. We went to our friends in epistemology and asked them this, and they said, oh, I don't know, that's also really hard. I have no idea. There is a theme in epistemology on expertise and what it means, but none of it is empirical. There is no data, none, in this whole literature on who is an expert and who isn't. They talk about stuff. And the change came in 1991. And I'm sorry, I've got a book up here too, because I've got the cover and it's the same size as the others, but it's not as good as the others. This is the seminal book by Roger Cook. He wrote off in 1991, Experts in Uncertainty, in which he said, well, expertise and expert judgments about facts ought to be a science and ought to be an empirical science. So let's test our experts. Let's give them questions and see how well they do. And see if we can assess a domain of expertise by their performance. And let's see whether weighting the experts makes a difference to the overall judgment of the group. And how do we aggregate those judgments if they disagree? Should we take the average? Should we take a weighted average? Should we take, and what kind of weighted average should we take? And so on and so forth. You start to think about it as a science. And he immediately ran into the problem. Well, for question one, I've asked how many eagles in this patch of forest. In question two, I said, what's the probability of a fire in this patch of forest? And how do I combine those things that have fundamentally different measurement scales? One is unitless, the other's got a number and number of eagles. And how do I combine those? And he thought about this and he broke it down into how confident you are and how frequently your judgments are close to the truth on some scale. And he called them accuracy and I don't know what it doesn't know what it is. He broke it down into two parts. Now, this is the first book written by, sorry about this line, I keep drifting off. The book in the middle is the first book written by a statistician on uncertain judgments. When we were asked this question all those years ago, we first went to our friends in epistemology and they said, oh, I don't know how do you tell you an expert's a good expert? So we went to our friends in statistics and they said, oh, because our Bayesian friends used prior estimates. And where did they get them from? I said, we said to our Bayesian friends, where do you get your priors from? Oh, it's a biological problem. So we went to our friends in biology who write models and said, where do you get your estimates from? They said, oh, that's a statistical problem. We asked a statistician. It's nobody's problem. It was nobody's problem. This is the first book written by a Bayesian statistician on how to estimate judgments, and they had this way of doing things which is mathematically correct. Well, they're both mathematically correct, but this is conventional Bayesian estimation. They want you to estimate a distribution, and they say here where is the median? Where are the quantiles? Where's the 10th and the 90th, and where's the 80th and the 20th? And they sit people in a room and they talk it over and they map out a statistical distribution through discussion. And so they sort of torture their subjects into giving them another. And I'll come to what we do later on. So, who's an expert? Fundamental question. We gave questions that were within a person's domain of expertise to about a dozen workshops. We said to people like this, here are 20 questions, are these reasonable questions? And if they were epidemiologists, as one group was, it was, what will the disease rate for this disease be in the population 5 years hence? Sort of question you have to ask if you're an epidemiologist, because you have to buy your vaccines 5 years in advance. You can't buy them yesterday or today because they have to take time to make, and they've got to make new ones, and there's a schedule. You have to get in line. And so you need to know roughly what the disease rate will be. And so on. Lots and lots of questions. We asked them of seed biologists, wheat biologists, epidemiologists, and veterinary scientists, frog biologists, a bunch of different groups. Once they thought the questions were reasonable, we then said, what score are you going to get out of 10? Give me how well you think you're going to do. You see the questions. How many do you think you'll get right? And then we got people in the room to stand up and, as though they were at a court law, and say what their expertise was. Publish what you remember of, all that stuff. And people would. And then we said, write down what you think that person will get out of 10. And they wrote it down. And the correlation between how you think you'll do on questions and how other people will think you'll do on questions, we did not expect the correlation to be that high. So the way that you think you're going to perform is very close to the way in which other people think you're going to perform. So these are deeply held beliefs about performance on questions of fact. It's a big deal. We really believe this to be true of ourselves and of others. And we're to ask them questions. And this result has been repeated many times. The correlation between how either I feel I'm going to do or other people think we're going to do and how we actually do is zero. It is non-existent. There's a hard thing for people to swallow. They go, no, can't do that. How can I have 30 years working on frogs and not being able to make better judgments as someone who's still an undergraduate? How's that possible? In fact, it's not impossible, it's persistent. It is universal. There was a project that I'll touch on later, run by the US government that we got involved in which 5 university groups tried really hard to find anything about people that will allow you to predict how well they were going to do at predicting things. And the only things, and so we looked at this from lots of different perspectives. There was a very charming Romanian mathematician who had a Bayesian approach to this, and he was basing it on the esteem in which you are held by your peers. His theory was that your peers can tell how good you're going to be at doing one of these estimated tasks. You can't do yourself necessarily, your peers can tell. It just bombed. It went nowhere. He was the first person out of the competition. It sounded like competition. First group to be eliminated. And he said, there's nothing wrong with the theorem, there's something wrong with people. It's very charming. You should take this home. There is no correlation between a person's ability to predict facts that matter and the esteem in which they held, their age, the honourable status they might have assumed, anything else. It ought to be humbling, especially for us, and getting towards the end-ish part of our careers, where we think we should know something. Anyway, I do recall sitting in a room with the chief vet of a certain jurisdiction, sitting next door to a brand new a brand new vet, she'd been out 12 months. And she did better than him on the questions. And he said, is there nothing to be gained from growing old? And she said, not a thing. All right. So our solution is anyone who understands the question, theory, data, and context, irrespective of qualifications, years of experience, or peer recognition, anyone who passes a test of performance in answering a handful of relevant questions is as good as anyone else. We know this, we should take this home, we should use it. I had a conversation this morning with a group from Oxford University who are going to do a whole series of assessments of the risks associated with artificial intelligence. Involves a lot of guesswork. They're going to use these groups, and they said, we're going to do this, we're going to do that. And of course, we need people who are experts. And I said, well, who's an expert? And I said, well, you have to know, you have to be a computer scientist or know about the mathematics of artificial intelligence. I said, well, what about if you're just an enthusiast? What if you buy the magazine Artificial Intelligence Weekly and just love it? Is that enough? They would know. They're wrong. So what does this do? It opens the door to a much wider set of people that you can involve in making assessments. It's more socially acceptable because you get better buying. That's a sort of fringe benefit. The real benefit is that you will improve the accuracy and the reliability of your judgments. They will be more accurate and better conditioned if you use a more diverse group of people. So you should choose people. So we use as proxies of worldview, gender, age, religion, background, culture, that sort of thing. And they're good, but we're really looking for different perspectives on the problem as well. So you want to choose the person who's going to be most likely to disagree with you. You want to choose the person that annoys you the most. And if they're not in the room, you're going to miss out. You should make an effort to get a perspective of different worldviews and perspectives on the problem, positions on the problem. So, why is groups proud? James Surecki, I presume most of you have heard of this book, not read this book, but he comes to this from the position that experts will disagree. In some instances, the experts all still agree, and sometimes in this question, the answer was yes, which is represented by the 100. And the question was, what is the likelihood that something will happen? And here the group felt that it was rather more likely than not to happen, and it happened. But they weren't very sure. Over here, both groups said, it's not going to happen. We're pretty sure it's not going to happen. And it didn't happen. Thing didn't happen. The right answer was a 0 in this case, the right answer was 100 in this case. That's a yes, that's a no. And here the group averages, they said it's really unlikely. They went, oh, sure, probably not, probably going to happen. So you get a range of opinions about questions of fact, and you can then subsequently evaluate them. But Surecki really was reflecting on a paper by Francis Galton, in which he got a group of people to estimate the weight of Knox, and the median value was perilously close to the correct value. And he thought, isn't that interesting? And he called it an acceptable outcome because half the people would say it's too low, and half the people would say it's too high. He chose so it's kind of a democratic solution to the problem of how heavy is the salt. It was very accurate. And he reflected on that. Now, this paper stood the test of time. This is an experiment on, well, how clever are these groups? If they're good at some things, they're good at lots of other things. This is an experiment in which you get a group of people that have IQs of 100, so average IQs. And we give them IQ tests. And we say, well, what would 3 people say? What would 4 people say? What would 5 people say? Increasing group size. And a group of about 15 people has an IQ of about 120, a very clever person. All composed of people who have exactly average intelligence on these kinds of tests. Now, groups are smart. Groups are smarter than individuals, just on simple things like that. But groups also can solve things. James Tao, Fields medalist, Australian, I should say. Now, so let's put this on the web. It's a solution to a geometric problem that had been around for a very long time, and you gave it to a group, and this is the number of publications each person had. Some of them had almost none. And this is the rating for the most significant comments they made. So some people had almost no publications, but made very significant contributions to the solution. They were enthusiasts. Some of them were amateurs in mathematics. And yet the group solved this problem in a few weeks. It had been on the books in mathematics for years. And they found the solution in a few weeks because they functioned as a group. They interacted, they swapped notes, they helped one another, they found partial solutions to partial problems, and the full solution revealed itself. They can also, groups have unfolded proteins, found the folding structure of proteins in structural biology. Now, you can't just get a group and think they're going to do well because of beliefs in inherent morality of the group. We all believe that we're going to be good and we're all going to try really hard to get this right. But we have shared misconceptions. We have stereotypes. We have illusions of unanimity and pressures on dissenters that we may well be unaware of. As a consequence, groups can substantially deviate from the correct answer, even when an average of a set of simple estimates would have approximated the truth. So a group think can drive a group away from the correct answer. So what we need structured question formats to avoid overconfidence and to avoid dominance effects, anchoring, framing, and motivational bias. This set of things is, in my experience, the set of things that most often and most influentially affects the judgments of groups. And so we need methods to anticipate those biases and to mitigate them. Now, how do we do it? This is where you have to actively concentrate. Okay, this is where the test questions come. If you want to know a fact, a number, a quantity that's not yet knowable, and you have to ask someone, ask them in this way, and you will get an answer that is relatively accurate, relatively well conditioned. You say, realistically, what do you think the lowest plausible value is? We ask them with these words and in this order because it works better than any other order and any other questions we've tried. And if you can come up with a better set of questions and a better order, we'll use it tomorrow. So this is an empirical result. This works best as far as we can tell. Realistically, what do you think the lowest plausible value is? Realistically, what do you think the highest plausible value is? What's your best guess? And then how confident are you that the interval you created from those highest captures the true value? And I could talk for another 20 minutes about why that works. But believe me, that the things that I've talked about previously have led to this solution. And then, if you're asking about a probability, you ask the first three questions and you discard four. It's really hard to think about, looking for me, what it means to have a probability interval on a probability. So just don't go there. Just forget the question first. And we put it inside a group judgment protocol. We recruit a diverse group. Talked about why. You get them to, you send them the questions and you get them to make the estimate, lowest, highest, best, confidence. They make an initial, private, and anonymous set of judgments. You send them into a facilitator who aggregates them in the sense that they display them as a picture, and they might even find the average. And then you send this picture back to the group and you have a discussion, a facilitated discussion. And the facilitator encourages people to examine the counterfactuals as a group. What would have to be true for this person to be correct? They're not on everybody else. Now I want everyone to think about, and what would have to be true for this lower bound to be plausible? What would have to be true about the world, about the data, about the reasoning, and what would be true, have to be true for this number to be correct? And so on. You have a discussion. And people revise their meaning of the interpretation of the meaning of the questions. They introduce new information, introduce their reasoning, and people listen to one another. And if people are convinced by the reasoning and the information of others, they'll change their position. And in 70% of the time, when a person changes their position, they move in the direction of the truth. And then you ask them again, can you please revise? And the aggregate of that second round is going to be more accurate, better calibrated than anything else we can find. and will also outperform the best regarded person you can find consistently and by a considerable margin. So if you are asking for expert advice and you ask a single expert, you've made a mistake. If you ask for a group of experts and they're not diverse, you've made a mistake. If you ask your group of experts to estimate facts or future events in an unstructured format, you've made mistakes, a host of mistakes. And you can avoid all of those mistakes without any extra work, just with a little bit of discipline. It's all you need. People say, oh, it's going to take too much work. It doesn't take any more work. In fact, if there are many questions, it's faster. It gets rid of a lot of discussion about the meanings of terms and about where evidence is going to fit and whose opinion matters. And people actually enjoy it a great deal more than an unstructured, informal, conventional approach to expert judgment. So here it is, the picture. I've questions, identify your experts, agree the meaning, do the 3 steps, aggregate, and then you might send the results. So how does it perform? Well, we've got to test this through IARPA, the Office of the Director of National Intelligence, and I have an email that I have framed that says the Director of the Office of National Intelligence in the United States wants to speak to you before close of business on Friday. I made it. So this was what the IARPA calls a tournament of data, and they do it called a tournament. They had 5 or 6 university groups. At the end of the first year, the first university group that's performed least well is cut. Second year, the next group is cut. Third year, the next group is cut. So you don't know how long the project's going to last. Sharpens the minds of postdocs. Really want to stay on the ball because it's a competition and your livelihood depends upon it. This is an unweighted linear pool of the opinions of US intelligence analysts trying to guess the outcome of geopolitical events, and you had to beat them to stay in the game. So it wasn't easy to stay in the game. In fact, it was quite hard. 2 groups got chopped in that first hurdle, including my poor friend from Romania, who said there's nothing wrong with my theory. Prediction markets, which we don't have time to discuss, did quite well. And what we call our Delphi groups, which we now call the IDEA protocol, also did really well. Now, the group that won this competition in the end was Philip Tetlock and Barbara Mellors, his partner, and Dan Gardner, who wrote this book together with Philip Tetlock on super forecasters. What they did was got 3,000 people, tested them, took the best 60, put them in groups like ours, and asked them questions. So they got people who are already predisposed to be groupers. That was a really smart move to a big group, winnow them down, and they called them super forecasters. We just got 300 people and didn't filter anybody and put them in our groups. And we did, and their performance was about a year. So they were noticeably better, hugely better. And we did it without having to filter out 3,000 people down to 60. We did it with just anyone we could get who was interested. So we had that definition of an expert. If you're interested, you're in. And these were important things to learn. But it took this project 6 years and loads of money, many tens of, and they sent us a dozen or 12, 15 geopolitical questions a month for 3 years, and we had to try and answer them. And they said, we don't care how you get the answer, we just want to know who does best. And we'll see who does best by looking at the outcomes. So it's a really good test, a serious test of performance. And we stayed in the competition until with Dan Gardner's group until the end. There's only 2 groups left at the end. And they outperformed us because they had better organised and better structured, but they essentially used the same methods, the same approach. And we then took our group, pulled out the best performers, put them in a group, and they were our super forecasters, and they did noticeably better. So we were able to replicate the result with super forecasters. So, I don't have time to go into this because we've only got about 10 minutes left. So, what works? Ask structured questions in different ways, consider counter arguments, revise original estimates after feedback, anticipate psychological issues, and use groups in a group structured format. So going back to the the questions at the start. Who's an expert? So it's anyone who understands the question of theory and data. These things don't help peer recognition qualifications. Diversity improves group judgments. How many experts do you need? 5 to 10, after which there's diminishing returns on accuracy. What's the domain of expertise? Understand the questions. And then how do you ask? You can really only get through 15 or 20 questions a day. You should measure performance by validating externally, by finding the answers. Should you weight your experts? Yes, if you have the data. We don't have time to go into that, but that does work. And different opinions should be reconciled mathematically. We're not looking for agreement. This is something you tell people at the start. We're not looking for you to agree with one another. We're not looking for consensus. We just want your best judgment, and then we trust the group. That's the secret formula. Model assumptions, model structures. We've only talked about parameters, if you like, numbers, this quantity, this outcome. We haven't talked about, well, is this functional relationship convex or concave? Or is it something else? How do I know? And what kind of structural relationships are there between two variables? None? Some? What form? Those kinds of structural assumptions are in the same bucket as expert judgments, and it has received no attention. Experts will sit in a room and dream up a model, and you are such a person, and people will go, okay, seems good to me. Yeah, needs to conform with what we know. I'm happy to go with it. We have no idea whether they work. And this is an example in which one of the modelers of Great Britain admitted we just talked to a few people. We would have killed fewer people. They had, instead of having a large group of diverse people look at their model and tell them about what they thought of it, they just, 6 guys got in a room. And of course, they were good modelers. They wrote a model and everyone believed it. And thousands of people died as a consequence to it. So this is going in lots of different directions, in the direction of peer review, eliciting model structures, improving intelligence assessments, predicting the replicability of scientific experiments, and so on. And it'll go other places, I'm sure. And it's the team that did it on the right. Philosopher, mathematician, psychologist, philosopher, mathematician, and biologist. And thanks. Well done.
So we have about 10